All right, so now we're going to get into laws of thermodynamics. And this is going to explain why a lot of reactions and biological processes happen in our bodies. So we're going to start with the first law of thermodynamics, and that says that energy cannot be created or destroyed. It can only change from one form to another. So if you look at this video right here, you can see that you've got wind energy that is pushing those turbines and actually changing and converting that energy into electricity that we can use. That's a perfect example of that first law of thermodynamics. Now, if we go back to the notes, you can see that I list that in living organisms, we've got our potential energy stored in our chemical bonds, and we can actually shift that into different types of molecules, or we can actually use that to power muscle contractions and things. One thing that's important is that energy does get lost in the form of heat, and that does not mean lost, because I just told you you can't create or destroy it. It just means that that's an unusable form of energy as far as we're concerned. Okay, then the second law of thermodynamics states that the disorder in the universe is continuously increasing, and that disorder is more likely than order. If you could see my house right now, you would totally support that idea because, man, is there some disorder going on. So that's the second law of thermodynamics. And if we want to think about this chemically, we can look at these water molecules that you see right here. So you can see that these water molecules are just kind of floating around and doing their own thing. They're not really organized in any way, shape, or form. And then if you look at this next slide, you can definitely see this is ice close up, and you can see how the molecules have been organized. So there are ways to organize things, and that's through chemical bonding. Okay. So now, if we look at the next little part of our notes, you can see we're going to talk about free energy. So free energy can be calculated to figure out how much energy is around to break or form a chemical bond. And so this right here, G equals H minus TS, is going to be the formula that you can use to actually figure that out. So G is going to stand for free energy, H is going to be the energy containing chemical bonds, T is the temperature, and S is the amount of energy unavailable because of disorder. So if you think about it, H, if we're talking about energy and chemical bonds, that's going to be order, right? And then temperature is going to be, if you think about it, if you increase temperature, the molecules are going to start bouncing around. That's going to be disorder, and then S is obviously disorder. So basically you're taking order minus disorder, and that's how you can get your answer for that. And so whenever you have a reaction, a chemical reaction, like anything we do in lab, then you're going to have a change in the free energy. And there's two ways it can go. You can have what's called an endergonic reaction, which is a reaction that cannot happen until you put energy into it. So the way I think about it and remember it is in, right? So endergonic is going to be one that requires energy to be put in. Now, an example of that could be one of those chemical ice packs if you've ever used them. So here you can see that the way these work is there are two chemicals inside of them, and what you do is you actually crush the one chemical that's usually in like really thin glass inside of the ice pack, and those two chemicals mix together, and all of a sudden it feels cold. Well, the reason that feels cold is because it needs heat in order for that reaction to happen, and it's going to be pulling the heat from your hand. So that's a perfect example of an endergonic reaction because it's using the heat from you in order to make that reaction continue. Now there's also exergonic reactions. And exergonic reactions are going to be ones that are going to release energy. What a perfect example, fireworks, right? Those are releasing heat and light energy, and they're doing that in order to, that's how the reaction is progressing. So that'd be a great example of an exergonic reaction. And so the way I remember exergonic is something exploding, right? It's giving off energy. Okay, so both of those types of reactions are going to happen in our bodies, and endergonic ones that require energy, are going to be one of the reasons that we eat sugar and things like that, because we need to power those reactions. An exergonic reaction would be like our muscle cells moving around, and those are creating heat, and they're actually creating movement, right? So that would be kind of an example of that. Now, activation energy is going to be how much energy is required for a reaction to proceed. And so on this PowerPoint, I've actually got a little graph here that can kind of show you what we're talking about. So here, in that black line is going to be how much energy is required for a reaction to happen. And so you can see that it requires quite a bit of energy and then the reaction will proceed, right? Now, if you look at the red line, that's the same reaction happening except an enzyme or a catalyst has been added. And what a catalyst does is it basically reduces the amount of energy that's needed, and so the reaction can proceed. Now, you've already done this in lab without even realizing it. One of the times you did it is when we were using the Benedict's reaction, and if you remember, that was the one that turned from blue to orange, but you had to heat it up and boil it for that reaction to happen. So the heating up and boiling actually brought the level down to this red line area right here so it can actually proceed. You also did it with the burettes when you were testing for proteins. If you remember, you added burette, but you had to add NaOH, which was going to be a catalyst, and that was sodium hydroxide, and that did the same thing. That just chemically helped that reaction to happen and brought that line back down to here. So in the next little section, we're going to talk about enzymes and how enzymes are going to help for a reaction to kind of go a little bit more easily. Hey everybody, it's time to start Chapter 8. Chapter 8 is going to be about energy and metabolism. So what this chapter is going to be is more of a prep for Chapters 9 and 10, because Chapters 9 and 10 are going to be about cell respiration, which is keeping us alive, and then photosynthesis, which is giving us the energy to keep us alive. So we're going to kind of get into all of those, but we need some basic knowledge before we get into that. And I'm not going to lie, these chapters aren't easy, so make sure you pay attention and really make sure that this makes sense, or you come with questions to class. Okay, so as you know, energy is going to be the capacity to do work. And so what we're going to do is talk about different types of energy and how we measure it. So let's see if I could go to the next slide here. That was pretty. Okay, this right here is going to be something that's called a calorimeter, and I am so sorry if you hear my dogs jingling their chains and wrestling, but it's raining and they are going insane being inside. So anyway, if we talk about the way we measure energy, this is a calorimeter right here. And so what a calorimeter does is tells you how many calories are in something. And calorie is a unit of heat. And what it's measuring is how much energy is required to raise the temperature of 1 gram of water by 1 degree Celsius. And so what you basically do is you take your food or whatever it is and you put it into this little cup right here, and then you incinerate it, and then you see how the temperature rises. And that's how a calorimeter works. Now, another way that we can measure how much energy is in something is with joules, and a joule is worth 0.239 calories. But we are going to probably tend to use calories more in this class. Okay, so there's two types of energy. One is going to be potential energy, and the other one's going to be kinetic. So in this picture here, you're seeing a guy who has potential energy with the ball. And the reason it has potential energy is because it's not moving, but it is at the top of a hill. So it has the potential to do something. Some other examples of potential energy that will apply more to what we're going to be talking about. If you think about gasoline, right? Gasoline is going to be something that can power something that moves. So that would have potential energy, as would a battery. A battery is also going to have the potential to power something. If we want to get a little closer to home, we can talk about this lovely molecule right here, which is a fat. And so every little line that you see in all of these different structures right here is going to be a chemical bond, and chemical bonds store potential energy. So that's why we're talking about energy, is because we're going to talk about the energy stored in chemical bonds. Now, what can happen is all of this energy that you see here can be converted into kinetic energy. And so what happens is, when we have fat stored, what we can do is start eating away at these chemical bonds and use that for energy. And that's why we always look at that balance of how many calories you take in versus how many calories you expend. Because if you take in less calories than you use, then your body's going to need to pull those calories from somewhere, and so it'll pull from these chemical bonds. Now, the other type of energy is going to be kinetic energy. So you can see here the guy has pushed the ball and it's going to be going down the hill. Now, I have another example of kinetic energy. This is going to be one of my crazy dogs you're probably going to hear during this little lecture. And so what happened was this morning I gave her dog food, and so that was potential energy because it had the potential energy stored in the bonds of the glucose that was in her food. And then that energy got transferred into kinetic energy, which you can see here, where she is running and chasing cars at the dog park, right? So that energy has changed to kinetic energy because now she's moving. It is insane. She is going as fast as the cars. The dog is crazy. If anyone ever wants to dog sit, you're more than welcome. So those are going to be the two types of energy that we're going to talk about a lot. Potential is going to be the potential to actually do something, so like gasoline, a battery, fats, and then kinetic energy is actually the energy of motion. Okay, so what we're going to do next is start talking about oxidation and reduction because these are going to be things that are actually going to be affecting keeping you alive, basically. So if you look here, you can see that we have two things. We have losing an electron and gaining an electron. Now, if you remember, electrons can't just hang out in the middle like, I don't feel like going to any molecules right now. They have to go from one to another. And so if one is getting oxidized, the other one is getting reduced. So remember we said Leo the lion, it says Gur. So remember Leo stands for lose, whoops, lose electron oxidation, and Gur standard for gain electron reduction. Now this is going to be super important because this is basically what is keeping you alive, and it's going to come up all the time because we have these little organelles in our cells called mitochondria, and the whole way that mitochondria work is by oxidation and reduction, just electrons moving. So basically when you die, those electrons stop moving, and that's as simple as I can put it. So in the next little section, we'll talk about how this actually works.